Hello everyone, this is my video series learning time series and forecasting. And I made this series for preparing for my midterm exam, and I will write here introduction. To time series and forecasting, and this is based on the textbook of Peter J. Rockwell and Richard A. Davis. And I read the second editions. All content we will talk in this series include 1. Introduction to time series, and in here we will given some example of time series objective the objective of time series, given some example model symbol time series model. Like zero min, Jan, and seasonal, given stationary, model, and correlation function. Find or estimation and elimination of chain and seasonal component. Part 2, we will learn more about stationary process. Is something like property of stationary process, properties, some more process like linear process, and AMA process. In 3 talk about ARMA process and some property like some property sample mean and outer correlation function. Into 5 forecasting stationary time series in the part 3 we will learn about ARMA model, the subcontent here. I will add them ourselves up to here later. In part 4 is spectral analysis. In part 5 we will learn about modeling and forecasting with ARMA process. In 6 is non-stationary and seasonal time series model. Part 7 is multivariate time series. Part 8 is state space model. Part 9 is some forecasting techniques. And the final part is some further topic. Okay. Today we will talk about some introduction to time series model. To who haven't hear anything about time series introduction. First, I will give some example of time series. A time series definition. A time series is a set of observation x t and each one being recorded at specific time t. And according to time or divide into time of time, time, discrete time, time series, the time series with the set I will call it T0. It's just a set of time here. T0 set of time. T0 is a discrete set. For example, when we observe in a fixed time interval, like it 1 second will record flex. Here is continuous time series. Continuous time series. This is often when the observation are recorded. And continuous over some time interval. Like 0 and 1 something. And first example, I will give example 1 is Australian red wine. So is record from 1980 to 1992, 12 years. Just to October 1991. And T0 concede 142 times. Like is record each month, January to October. October 1991. An asset of an observation. May art uniformly space-time interval. I won't draw this here. It's in the textbook. In example 2 is All-Star baseball game. From 1933 to 1995. The time series does include two values, xt, or 1 if the National League won in year T, and -1 if American League won in year T, and the result like this. I will scrap here from 1940, 1950, 1960, 1970, 1980, 1990. The result here like this. In 1994, the National League 0 here, Aces 0, 1 here, -1, like this, and then below the American League won like this. This here the graph arise in 1990. It's like this, and this degree here, and from 1960 to 1970. In overall, we can see here the national list have more than American list. And some another example we see in this cycle, accidental death in USA. An example 4, in an example of signal processing has the equation with t from 1 to 200, and t here is sequence of independent normal random variable. And mean of this is 0, and variance is 2.25. Such series will refer some signal, and plus this we call it noise. This signal is a smooth function, and given this problem here, given the data, how we can define the signal, how to define this. Another example is population of the USA, and number of child a year in the USA. These examples we will consider and recall in the next two is objective of time series analysis. Is the example in section 1.1 are extremely small sample from the multitude of time series encountered in field of engineering, in science, in sociology and economics. And our purpose, the purpose of this book is to study the technique and drawing in inference from such theory. And before we can do this, however, it is necessary to set up a hypothetical probability model to represent the data. After an appropriate family of model has been chosen, it is then possible to estimate parameters, take for goodness of fit to the data, and possibly to use the fitted model to enhance the understanding of the mechanism generated in series. Once a satisfaction model has been developed, it may be used in variety of ways depending on the particular field of application. The model might be used in simply to provide a compact description of the data. We may, for example, we able to represent the accident death in the example 113 as the sum of specified chain, and this is the random term, the interpretation of economic statistics such as unemployment figures. It is important to recognize the presence of seasonal components and to remove them so as not to confuse them with long-term trends. This process is known as seasonal adjustment. Other applications of time series model include separation or filtering the noise from the signals, and in example 114, filtering noise in signal and predict the feature value of a series such as the red white cells in example 1, the population data in example 5, testing hypotheses such as global warming in the using recorded temperature data, predict one series from observation, another predict future sale using advertising expenditure data, and controlling future values from a series by adjusting parameters. Time series models are also useful in simulation study. For example, the performance of reservoir are also useful in simulation study. For example, the performance of reservoir depends heavily on random daily inputs, water of system. If this is a model time series, then we can use a fitted model to simulate a large number of independent sequences of daily inputs. Knowing the size and the mode of operation of reservoir, we can determine the fraction of simulated input sequences that cause the reservoir can run out of water in a given time period. This fraction will then be estimate a probability of emptiness of the reservoir at some time in given period. This is the objective of time series, and we will change to part 3 in some simple time series model. An important part of the analysis of time series is selection of a suitable probability model or plot a model for the data to allow for the possibility unpredictable nature in the future observation. It is natural to suppose that the observation xt is a real-time realize value of a certain random variable except t. Certain random variable except t. The first definition in this part, a time series model. Time series model, and model for observation data. XT is a specification of the joint distribution. Specification of the joint distribution. Or possibly only the mean and the covariance of a sequence. A sequence of random variable big xt or which xt is postulated to be valuation remark here. We shall frequently use the term time series to sum series, not the model, to mean both the data, and the process. Of weight valuation. And to clarify this definition, we need to know some term here, like joint distribution. A complete probabilistic time series model for sequence of random variable sequence of random variable x1, x2, etc. would specify the joint distribution of random vector in a vector like this. X1 to just again, or n 1, 2, or equivalently the probability. This is joint probability, P of at smaller than xt1 xn, and negative infinite. This small t finite, both positive or negative. Such a specification is rarely used in time series analysis unless the data is generated by some well-understood simple mechanism. Since it's general, it will contain far too many parameters to be estimated from the available data. Instead, we specify only first and second order moment of joint distribution. Examples: expected values. Expect we consider like expected value of 80, expected of 80, and expected of product like xt plus 8 and xt where t to 1 to 8, and focus on the property of sequence of xt that depend only on the such property of xt is referred to second order property. In the particular case where all joint distribution are multivariate normal, the second order property, second order property and this is first order in the particular case where all joint distribution are multivariate normal, the second order properties of xft completely determine the joint distribution and hence give a completed probabilistic characterization of sequence. In general, we will lose a certain amount of information by looking at time series to second order spectacle. However, as we saw in chapter 2, the theory of minimum mean square error linear prediction depends only on the second order properties, thus providing further justification for using the second order characterization of time series model. Next, given some zero mean model, mean in distribution is like wait an example. We talk about IID noise. IID noise meaning independent and identically distributed. IID distributed here is distributed random variable, and zero mean it mean this is the simplest model of time series and there is no chain or this is no component here. Independent. Okay, it's mean I deny x1 to xt if I see e of x and xi is must be equal to 0 in cos it 0 mean, and cos this series independent, it means independent between two component in a series xi and xj is must be 0 for I different to j, and is normal distribution sigma square. And here we can calculate the joint probability function to xn cos of the independent property. We can split them to the product of its probability. And call this f x of 1 to f x of n, and where n is the cumulative distribution function. I will call this the CDF in later, and it's the identical distributed random variable x1, x2. In this model, there is no dependence between the observation. I talk this below. In particular, for all 8 bigger than 1 and all x1 to the xn, then probability function is with the condition x1 xn is equal to and this showing the knowledge x1 to xn in no value predicting the behavior of the xn plus 8, and given the value x1 to the xn, the function f dot minimize function f minimize square error is f plus f of x1 to xn in is in fact that's an identical zero. And although this means that IID noise is very unique intersingle set for forecaster is play an important role in building block a more complicated sum series model. It's too late tonight. I will return tomorrow.